As we begin to dive into the various algorithms available in machine learning, a great place to begin is linear regression, which is probably the birthplace of machine learning. With linear regression, we use a straight line to describe a data set. And in simple terms, the goal of linear regression is to split your data in a way that minimizes the distance between the regression line and all data points on the scatter plot. This means that if you were to draw a vertical line from the regression line to each data point on the graph, the aggregate distance of each point would equate to the smallest possible distance to the line. And the technical term for the regression line is the hyperplane. And so this is a term you'll hear throughout the course. And it is essentially a trend line. And we won't really delve into the math of how the line is determined, but it is worth noting that in our example here, we are using 2 dimensions for the sake of simplicity, but you'll typically have more features. And the same principles apply to higher dimensions, though things can get much harder to visualize beyond 3 dimensions. So remember that when you have one feature, we refer to it as simple linear regression, but where you have more than one feature, it's called multiple linear regression. And we won't go into the math in depth, but the formulas for each are expressed like this. And linear regression makes a number of assumptions that don't always stand true. The first assumption is that there is a linear relationship between the target and the features. So if your data looks like this, you're probably all right, but what if it looks something like this? If we use simple linear regression, you'll see that it doesn't fit really well. In the middle, you can see that you've got data underneath, and as you go further, the data goes above the line. So let's see how we can fix this. Well, we can try to use polynomial regression. So instead of using linear regression, we can conduct polynomial regression. And as you can see, in this case, it fits perfectly. So what's the formula here? Well, the formula would look something like this. And if you look at the formula, you can see that we're using a square here. And the parabolic effect in the curve is created by the use of the b2x1 squared. And that's where polynomial regression varies from multiple linear regression. And which approach works best depends on your data set and what you're trying to do. Typically, a data scientist might start off by trying out simple linear regression or multiple linear regression and seeing how it works. And sometimes they'd find that approaches like polynomial linear regression would work better. And an example of this might be if you're trying to model the spread of a disease, there is the viral growth or parabolic growth effect that you can try to model using polynomial linear regression. Let's now talk about the black sheep in the flock, and that is logistic regression. And don't let the name fool you, because while this is a regression model, it is used for classification. And logistic regression is often used for binary classification, where there are only 2 classes, where essentially the model makes a probability about whether an event will occur or not. But it is possible to use this method with any number of categories. For example, if you are trying to assign handwritten digits a label between 0 and 9, or using facial recognition to detect which friends are in a Facebook picture. And this model is essentially a modification of linear regression that makes sure that the output is a probability between 0 and 1, and it applies what's called a sigmoid function, whereby the graph looks like a characteristic S-shaped curve, and the function essentially squashes values down between 0 and 1 and results in a curve that looks like this. So with this approach, if say you are trying to predict whether an email is spam or not spam, what you would do is set a probability cutoff or threshold for a positive result. For example, we could determine that if our model thinks that the probability of this email being spam is higher than 70%, then let's go ahead and label it as spam. Otherwise don't. And this threshold that we set will depend on our tolerance for false positives and false negatives. So if you're trying to do something critical like diagnosing cancer, you'd want very low tolerance for false negatives, because even if there's a very small chance that the patient has cancer, you'd want to run further tests to make sure. So you'd set very low thresholds for a positive result. However, if you were running a model to try to detect fraudulent loan applications, the tolerance for false positives might be higher. All right, that brings us to the end of this lecture on regression. We've covered simple linear regression, multiple linear regression, polynomial regression, and logistic regression, which is a form of classification. See you in the next lesson.